Hi there, my name is Joseph Jackson. I am the principal investigator for REACT-UCA, a Naviair Phase 2 being performed at Scientific Systems Company. REACT-UCA is a collision avoidance solution applied to unmanned carrier aviation. SSCI prides itself in developing autonomous systems across a variety of domains. We are a small business located outside of Boston, Massachusetts, focusing on research and development using advanced perception, decision logic, and machine learning algorithms to solve some of our country's most challenging autonomy-related technical problems. Our solutions have been applied to land-based autonomy, unmanned aerial vehicles, maritime systems, including underwater and surface vehicles, and we have a payload on orbit as we speak for a collaborative space-based autonomy mission. Our development in collaborative mission autonomy is applicable across multiple domains. Our first technology breakthrough that resulted in field testing of a large network of autonomous vehicles was in the maritime systems domain under the DARPA CNAV program in 2008. Since that early work on collaborative network of autonomous underwater vehicles, we have expanded our focus areas from feedback control, sensors and signal processing, innovative algorithm development, and networking into the broader realm of collaborative mission autonomy architecture that is being applied and fielded successfully for drone missions, swarm and satellite missions, terrestrial autonomy, and maritime applications. SSCI's approach to autonomy brings a continuous maturation from basic core autonomy through intelligent cognitive mission autonomy, where the agent is no longer just performing mundane tasks such as waypoint control or assisting in mission planning, such as solving for optimal search patterns. Instead, it has been designed to work as part of a team, composed of human and autonomous agents, seeking to understand mission objectives and react to real-time commander's intent. With fully autonomous situational awareness, dynamic decision-making, and multi-vehicle control, the autonomy enables AI/ML adversarial reasoning, learning, and prediction for an overall improvement in the mission effectiveness. SSCI has had programs enabling each of these levels of autonomy, and we are pushing the envelope to increase our TRL at every functional level. The challenge addressed by REACT-UCA is to develop a collision avoidance capability for autonomous tanker aircraft based at an aircraft carrier, such as the MQ-25 Stingray. The need is to have an integrated sense and avoid capability that can safely mitigate risks in dense airspace operations around the carrier, in transit to the mission areas, and during tanking operations where maneuverability is temporarily limited. We take a strategic collision avoidance approach for planning over a longer time horizon, and a tactical collision avoidance approach for cases when loss of separation has occurred. As stated in the solicitation, desired is a collision avoidance solution that has strategic capabilities to plan ahead to preclude conflicts, and that works seamlessly with a tactical capability to resolve an actual imminent conflict that could not be precluded through the strategic capability. During our studies, we have considered multiple scenarios involving higher aircraft density in the stack around the aircraft carrier, transit operations where threats due to non-cooperative intruders must be mitigated, and during refueling operations where dynamic mission constraints affect the collision avoidance timeline. In this operational view, we illustrate the types of zones where REACT-UCA provides estimation, prediction, and optimized maneuver recommendations for the refueling tanker. Our primary goal is to mitigate the risk of near mid-air collision, but we also try to reduce the frequency of loss of separation between aircraft. REACT stands for Robust Encounter Avoidance and Conflict Resolution, and here is applied for unmanned carrier aviation specifically. Our design approach for REACT has been to build it within our autonomous SAA performance characterization tool we call Aspect, so that even in the design stage, we can analyze how well we are meeting our performance goals. As shown in this high-level system diagram, we can insert vehicle dynamics in the gray box with a candidate sensor suite, and then use our multiple aircraft encounter scenario generator, shown in red, to design approach geometries to challenge the REACT system. At its core, shown in green, REACT fuses tracks from available sensors, then computes the probabilistic risk of loss of separation, and provides a score of the likelihood of near midair collision, or NMAC, and then evaluates candidate avoidance trajectories according to rules of the road, probability of success, and potential cost to implement. The blue boxes designate component-level performance analysis for the tracker and the prediction modules, as well as the system-level performance evaluation that produces metrics such as overall success rate, risk ratio, the time series of temporal and spatial separation maintained. The design of our autonomous sense and avoid performance characterization tool allows us to perform comparative analysis of different SAA designs quickly, which can be leveraged to inform sensor selection for future SAA systems. We use Aspect under this program to help establish a safety case compatible with the anticipated blend of MQ-25 missions. Our current REACT Phase 2 SBIR expands upon more than a decade of sense and avoid development. In the fall of 2021, we derived specific sense and avoid performance requirements to meet the target level of safety metrics for unmanned carrier aviation. During the spring and summer, we finalized the decision logic to meet the mission criteria and tested that logic through large batches of simulated encounters for statistical analysis. Since the fall of last year, we've been testing REACT-UCA on open-loop flight data recorded from multi-vehicle aerial encounters collected by SSCI's data collection team. We anticipate Phase 2.5 to prepare for onboard flight tests through software hardening and software-in-the-loop flight tests. We have found REACT to be highly successful, mitigating 94% of the loss of separation cases. When loss of separation does occur, we have demonstrated that REACT mitigated 100% of the near midair collisions. This result demonstrates that REACT exceeds the target level of safety. I have already mentioned that REACT operates as both a strategic planner and a tactical planner to accommodate long and short-term intruder time horizons. When the estimator recognizes a threat is close, for example within 30 seconds of NMAC, the tactical planner immediately determines an avoidance trajectory optimized for the approach geometry. The strategic approach is on a longer time scale, for example up to 2 minutes. In this case, a minor course adjustment is suggested which meets the minimum operational performance standards for sense and avoid systems and does not violate mission performance. The backbone of our approach is in the forecast module, where our software produces probabilistic reachable sets based upon MIT Lincoln Lab's uncorrelated encounter model. Using a maneuver model has been shown to result in 4 times fewer false alarms than traditional linear propagation models. REACT is sensor agnostic, and as a software solution enables us to fuse detections and tracks from multiple sources in real time. Thus, it can be compatible with low swap C designs for existing vehicles and provide justification for sensor selection for future systems. Since our approach is built and tested within a performance characterization framework first, we have produced high-confidence results across multiple scenarios with reduced flight tests required. So where do we go from here? To be ready to transition to the fleet, we expect REACT-UCA to be validated in closed-loop system tests on a surrogate platform. We anticipate support from NavAir for platform selection and interfacing with the vehicle and its threat detection hardware. Our flight tests go through 3 increments. First, we test based on recorded data. Second, we perform open-loop flight tests to validate detection and declaration. Finally, we hold closed-loop flight tests demonstrating the maneuver recommendations. We have appreciated the support from John Leonard at NAWCAD Flight Dynamics and the PMA 268 Advanced Development team members. We have also been pursuing a path forward, partnering with vision-based sense and avoid innovators at SSCI, who have provided flight test data from the OASIS program, where SafeC is being designed for an MQ-8 Fire Scout solution. SafeC provides collision threat detection and evaluation for the MQ-8 Fire Scout using vision-only sensors. Because it's a passive vision-only sensor system, it does not include an estimate of range, but rather a temporal proximity between vehicles. We have designed a method to use time to contact as a trigger within our approach models to mitigate collision threats. I appreciate your support and curiosity about our sense and avoid solutions, and would love to talk with you more about your own emerging needs for autonomous systems.